Good afternoon, everyone. Very warm welcome to this webinar. Today, we are very happy to be here and to talk to you about how you can save energy and reduce carbon emission in HVAC. We are very happy to have a very good program for you this afternoon. And my name is Anna Hall. I'm the Global Business Development Manager for Sustainable Cities within Alfa Laval. And to my help today, I have my colleagues, Morten Alm, who's responsible for the business development of HVAC, and Ismail Usman, the Global Business Development Manager for Energy Hunting Partners. And we are very happy to take you through this schedule today. I will start to introduce you to the Alfa Laval and different sustainable solutions and how we work with sustainability and how we can help you. We will move on to reach lowest operating cost with certified performance by Morten Alm. Ismail Usman will then take over and he will talk a little bit about Alfa Laval product branded features and then energy hunting within HVAC and main applications. So, very happy to share this afternoon with you. This broadcast will go out to Poland, Latvia, Lithuania, Estonia, and Southeast Europe. Warm welcome, all of you. And we will also record this session. So if you want to see it after the meeting, it will be placed on a channel so you can see it afterwards. We will have a question and answer Q&A in the end of the session. And so please, if you have any questions, please write them in the chat. And I will be the moderator of this event and I will take care of your questions in the end of the session. So feel free, put in your questions and we will answer them in the end of the event. Very, very warm welcome. So, my name is then Anna Hall, and I'm responsible for the business development area of sustainable cities. And this is a very, very interesting part. It's actually one of EU 5 missions. It's that important. It's one of the pointed missions to handle the energy crisis and the climate and challenges we are in, and to take this and put forward the solutions together. So, but first, a little short about Alfa Laval. So Alfa Laval, we are a big company that are operating globally. Actually, we are celebrating 140th birthday these days. It was founded in 1883, the company. I come from the thermal part of the company, taking care of heat transfer, energy efficiency, and we have been working with heat transfer almost for 100 years. So we have almost 18,000 employees around the globe. We have sales companies in 55 countries and other representations in 45 countries. We have a large amount of service centers, so we can have clean heat exchangers and high performance all around the globe. So we have more than 100 service centers and we have a turnover around 4.5 billion euro. Of course, the UN global goals are very important to us. We believe that everyone needs to contribute in order to save this world, and we're happy to do it, and happy to do it together with you. And we have a number of production facilities around the globe, 37 major production units where we produce our products. And our 3 main areas are heat transfer, which we are going to talk about today, energy efficiency and HVAC. We also do separation and fluid handling. We serve most industries. We have been in the business for almost 140 years, or actually 140 years, and we have a long-term relationship with a number of different areas and different customers and what we see now is all these areas are more and more working together, solving the challenges of the world today. For example, HVAC, sustainable cities is just one part. We are working actively with data center, wastewater treatment, petrochemicals, food and beverages, machinery, marine and diesel, and so forth. So our scope is large, and we try to cross-fertilize the knowledge between these different areas, which I think is very important for the future. And what is also very important for the future is how we choose to collaborate. And us living in Europe, we have had a huge energy challenge the last year now, and we are also, of course, committing to what we need to do in order to not only solve the energy challenge, but also the climate challenge. So with the Paris Agreement, where almost over 200 states have signed globally, we think this is a very, very important initiative to collaborate, set the framework, set the rules, set the actions, and to get on moving to a better place, not heating the earth more than at the maximum 2.0 degrees, preferably 1.5 degrees, but I think it's challenging since we have already reached a temperature increase of 1.1 degrees. So Alfa Laval, we're a big company. If you're big, you need to be nice, and you need to be forerunner, take the challenges seriously. So Alfa Laval is, of course, committed to the Paris Agreement. And we have a statement that we will be carbon neutral by 2030. We are working very hard with this internally, but also with our customers and our suppliers. So what does this mean? This means that we will be net zero within scope 1 and 2, that is in our own production facilities, offices, buildings, and so forth, and also the energy we use, and a 50% reduction in scope 3. That means together with our suppliers and our customers, we will decrease by 50% to 2030. And we think this will have really nice rings on the water and affect number of companies. And we do this preferably by collaboration. We think collaboration is very, very important. But we, of course, then work together with big companies reaching net zero together internally, but also we work very, very close to our customers. So our sustainable offering is that we make existing industry and cities more sustainable with our products. Now talking, I mean, the whole product range, but focusing on heat transfer and energy efficiency. We have the products, we've been working with it for many, many, many years. What we also see in Europe now, coming to the energy challenge, coming to the Paris Agreement, we need to work with energy efficiency, and we need to work in a more holistic approach. Of course, Alfa Laval is also a change agent. We work with the clean energy initiatives, and we work with the circularity. So when it comes to the clean tech business development areas, we have chosen a number, and important for us is, of course, green hydrogen, where we think will be a very, very important source for energy in the future. In order to decrease the carbon, it's not enough just to change processes. We also need to work with carbon capture. Energy storage will be a very important component for the future. Data centers is our time boilers. They are huge energy providers. 99.9% of the energy coming into data center going into waste heat or reusable heat, a very important source for solving the energy challenge. And also distributed power generation, renewable fuels, and chemicals. So Alfa Laval has a strong future-oriented development program within Alfa Laval and together with collaboration partners. So, but when we talk about sustainable cities, what do we talk about then? We talk about the holistic approach. We talk about energy efficiency and to reuse heat. What we have been doing so far is, for example, helping one industry with energy efficiency, reusing heat within the site, or we have been looking into one building, reusing heat in the building, doing very, very efficient heating and cooling solutions. But what we see now is that we need to have a holistic approach. We need to work with sector coupling. How can we reuse energy? Half of the energy in EU is going up a cooling tower or down into a lake or a river. This is crazy. And we also know that the energy consumption of the world, half is going to heating and cooling solutions, and half of that is industry and half of that is buildings. So buildings and sector coupling is of great importance. And we that belong to EU, we see now that there are coming more and more thorough and harder laws, for example, on emission trading systems, both for buildings from 2027 and on industry for 2026. So I think there is a new business case working to reuse heat. And with our knowledge doing this for 60 years, reusing heat for energy companies, we really would like to hold hands with our customers and develop this offering even further. In a sustainable city, we then need, in order to reuse the heat, we need to work with flexible and efficient energy systems. So energy systems, we see the trend. In Sweden, we have 50% district heating, for example. We see a very low grade of district heating in the rest of Europe. And this is, of course, coming up now, not only with district heating, but also renewable in district heating. And I think all of you are aware of this transition and how we are talking about more and more renewables and the flexibility. Going away from fossil fuels, reused energy from industry, reused energy from, for example, wastewater treatment plants. But in this then area, with the heat networks, we have the flexibility of many different solutions. So not only then the energy systems like heating, cooling, but also then the new fossil-free energy sources that could be geothermal, for example, solar thermal, reuse of waste heat, or a heat pump on a wastewater treatment plant. For district cooling, it can be free cooling, for example. And this always in balancing with electricity systems. So we use electricity when we have to, for example, in the green transition of process industry or transportation, but heating and cooling, we could definitely reuse the heat. So the best energy is the one that is not used. The second best energy is the one that is reused. And also working more and more towards reusing the heat in buildings. Energy efficient buildings is a big area within EU where we need to work with preparing for heat networks and also updating energy solutions when it comes to heating and cooling to environmental friendly heating and cooling solutions are very effective and work with energy efficiency all throughout the whole user case, from production, distribution, and to the end user. So looking at these areas then, flexible and efficient energy system, district heating is of great importance on all lips in the European Union right now, and UK, and the next generation we see there is the low temp grid coming. That will then also enable more energy sources to connect. For district cooling, we see free cooling as a free source of cooling, not using electricity, and this is also coming in place. And cooling is coming more and more, and investment of cooling both in new buildings and also when renovating. There is a big demand, even in Sweden, that is a cold country. We see a big demand. When it comes to the new fossil-free energy sources, as we talked about, we see the waste heat recovery, as much as 25% of the district heating in total in Europe could come from be supplied by waste heat from industry, and then in addition to then we can use the urban waste heat such as data centers, metro station, buildings, wastewater treatment plants, and so forth. We also see there is a need for industrial heat pumps to balance the energy systems and come in with right temperatures and reuse also heat at lower temperatures. Geothermal heating and solar thermal heating, of course, of great importance. And geothermal heating, we see a lot of big initiatives, money coming in many different places, seeing how we can use geothermal heating as a source instead of fossil fuels. And I assume many of you already are in this field and are looking into how to find sustainable solutions within geothermal heating, both deep geothermal heating and the more shallow geothermal heating. And when it comes to energy efficient buildings, we work with energy hunting. Ismail will talk a little bit more about that. Of course, substations connecting to district heating, district cooling is of great importance, and how to prepare for this, both new build houses, but also when renovating. Pressure breakers, high-rise buildings, and in large systems will be of great importance. And of course, then in other applications, we are looking into heat efficient solutions, for example, for swimming pools, spas, and sauna, and greenhouses. More luxury parts, but important, that actually are taking a lot of energy and absolutely could be driven by reused energy. And Alfa Laval, also with some of our big system builders, we are into and developing efficient air conditioning and individual heat pumps for residential use. So these are the fields we are working with. So in all these applications, you will find an Alfa Laval heat exchanger, and you will find a very deep, broad, long-term knowledge that we are very happy to share with you. So don't hesitate to reach out to us to discuss more around what can Alfa Laval do in order to lower the carbon emission in HVAC and to provide a sustainable city solution to your customer and to your solution. So the lower carbon footprint and a lower life cycle cost goes hand in hand. So if we decrease the carbon footprint, we are following the Paris Agreement, we are taking the energy challenge and the carbon emission challenge for real. We are also doing nice things for our wallet. We are absolutely lowering the life cycle cost. So this is a nice win-win situation. So let's work on that together. And also very important, the electricity won't last. We need to use electricity when it's really demanded. Transportation, for example, or the green transition in the process industry, for example. So let's heat our buildings, our showers, and our city consumption of comfort heat with reused heat, or maybe cooled by free cooling. This is of great importance to take responsibility for the future and for our kids to come, or grandchildren to come. So just the last summing up slide around Alfa Laval and climate neutrality. We definitely think that energy efficiency is the #1 solution to the energy challenge. We need to work with heat exchangers and heat pumps, both individual and industrial heat pumps. We need to reuse the heat in industrial excess heat, and we need to find flexible networks so we can use the urban waste heat as well. We do believe in the future, in the clean tech solutions. We do believe in green hydrogen, carbon capture, energy storage, and so forth. And we do believe that we need to do this together. So in industry collaboration and research, we are having a number of initiatives. For example, the energy efficiency movement. You can Google that. You will find Alfa Laval and ABB started it, 2 COPs 26 it was started together, and we're now over 300 companies joining the movement on working with energy efficiency in our individual companies, doing a big footprint in the world. We do have a collaboration program with SSAB, for example, around Concept Zero, the first heat exchanger that is carbon neutral, and our aims to have that produced and up and running by 2030. We do work with the standard certification. HRI is very, very important. Morten Alm will tell you more about that. And we also acknowledge that competence and education is very important. There is a lack of resources in this huge transition. So we are really in this together. And the last point, it's solution on a system level. We do need to work system thinking. We do need to work with networks, waste heat recovery, and excess heat, and to reuse heat in order to solve this challenge together. Thank you so much. I will now hand over to Morten Alm, and he will give you how to reach the lowest operating cost with certified performance. Welcome, Morten. The floor is yours.
Thank you very much, Anna. And welcome. It's nice to be able to be here today as well. So, as said, I work together with Anna and Ismail in the team of Global Business Developments in the HVAC sector. So, been focusing a lot on district heating, district cooling, free cooling, excess heat, and so on for many years now. But today, the topic that I will be discussing or talking mainly about, or actually only about, is how to ensure that you get the efficiency that you have calculated for a specific project. And that's, as Anna already mentioned, is called certification. That is the best way to work with certification programs, which I will cover during the next 25 minutes roughly. So this is a known problem that we have seen for many years. There is a huge challenge for a customer in this industry to actually interpret what data we as suppliers give you. You specify something and then you validate. A customer validates in the project, typically comparing quotes from different manufacturers, and there is a key how to validate. And most commonly, the data that is used from specification sheets from the equipment to validate that you have received the same performance from different manufacturers is the surface area when we talk about plate heat exchangers. That is something we see more or less everywhere. But if you don't know technology in heat transfer equipment, such as plate heat exchangers, it's extremely hard to tell if the data is actually accurate enough that you get in the tech spec. I think I've been supporting, I don't talk about hundreds, I would more or less say thousands of projects now, and unfortunately it is very true. We see this trend everywhere. Surface area is the major factor that is being compared, but in reality the data you find in the technical specification from any manufacturer cannot be trusted, unfortunately. So what we see typically then is, surface area is what is being compared. But if you don't know the technology behind what brings the surface area for a specific duty, as we call it, that the heat exchanger should do, then it's very hard to tell if the area is correct or not. We talk about in the industry, if you have a good fit for the actual duty. Different type of applications demands different type of heat exchangers, and what we work with is basically the physical properties and the dimension of the heat exchanger. For instance, for a cooling unit, you would need a narrow plate distance in between the plates of a heat exchanger, and if you get that or not, it's not given in the technical specification sheets. So it's extremely hard to tell if you actually get the performance that you have requested. And as a background, or as a consequence of that, basically, when it's hard to determine and there's high risk that you don't that you are not able to tell if you got the right thing. There is a window of opportunity for people to be creative. And what we've seen over the last even maybe 20 years is basically in the HVAC industry, there has been a trend to apply something that we call a market tolerance. Basically, there is a sizing tolerances applied in the market, and it's very common that you see that the actual unit that is delivered might deviate half a degree on the temperatures, outlet temperatures, and the pressure drop might be 10, 15 kilopascal higher than what was specified and promised in the technical specification. That is, I would say, what you can take for granted basically for an HVAC design on the market today, unfortunately. So if we work with an example, this is a building that is using aquifer storage for generating free cooling or heat source for a building. You see here we take from the wells or from the ground source 8 degrees, which is run through a heat exchanger to generate 9 degrees supply temperature to the building for the cooling loop. Then on the return loop, we have from the building to the heat exchanger, we get 14 degrees, which then turns into 13 degrees, which is re-injected down to the bedrock. So this is the duty that the unit has been specified to do, which we then describe right up like this: 14 to 9 on the hot side, 8 to 13 on the cold side. This is what was specified in a project, quite common setup in, for instance, in the Nordics where I live myself. And this type of installation would then typically have a heat pump or chiller as well to support the free cooling, and in the winter time to use it as energy source. So if we look into this specification that was written like that in the market, this is what was specified from the consultant. We talk about LMTD, so the average temperature difference between the hot and cold side. As you see, it's 1 degree on the left side and 1 degree on the hot. So the average temperature difference between the hot and the cold is 1 degree. When we make it, if anybody makes a design, then we use that as a reference. To perform this duty, we need 100% surface area. But what about the market tolerances that has been applied in the market? So if we look at the typical optimization of using these tolerances, you will see instead of having 9 degrees, you will get 9.5. On the cold outlet, you will have 12.5. So this half a degree. So we, in the bottom, we see we get LMTD of 1.5 instead of 1. So the average temperature difference between the hot and the cold side is now 1.5 degrees. So why is this implemented in the market? If we have the plate pack of the heat exchanger or the surface area of the heat exchanger, by shifting a little bit the temperature with this half a degree, actually the demand for surface area in a heat exchanger would be reduced by 36%. And this is, of course, the reason. The equipment becomes cheaper to purchase, and you can have a better price optimized quote for a customer. Unfortunately, again, this has been a trend for a very long time, and it's nothing that we want to do for the future. Hence, we work with performance certification instead. But of course, you see that 36% less surface area means that the heat exchanger, of course, would be lower in cost, in investment cost. But it comes with a cost. So what is the cost for this cost optimization then? If we look, the initial design was made like this: 8 to 13 on the well side, 9 to 14 on the building side. If you have a unit that then is designed to actually deviate 0.5 degrees on the temperatures, what will happen in actual operation? So the building side, the cooling loop for the building will still need 9 degrees. The operating system of the cooling loop on the building will ask for 9 degrees. And of course, then you would need to get those 9 degrees, you will have to run more water through the heat exchanger on the cold loop. More water on the cold loop means that the temperature going back to the wells is also shifted. So instead of having 14 to 9, 8 to 13, you will now have 14 to 9 on the building side, but on the well side, you will have 8 to 11.8. So there's a quite big temperature deviation going back to the wells. And of course, increasing the flow rate, you push through more water through a heat exchanger, and the price for this is the pressure drop. So the pressure drop is increased quite rapidly with a flow rate of through the heat exchanger. So in this particular case, the pressure drop increased by 60% roughly when you operate it with higher flow rate and less plates in the heat exchanger. And of course, this the increased pump capacity drives euros, of course, investment cost, more pump head drives more electricity, costs more money. But of course, it's also influencing the carbon emissions, more energy consumption or electricity consumption, which drives more carbon emission. So all in all, this tradition of market tolerances have been driving higher energy cost in the market. So sometimes we get this response then when we talk with customers about it. Well, they then say, well, it's only when at design conditions that you reduce or increase the pumping power, but that's not true. Of course, the heat exchanger which is underperforming at the design criteria will be underperforming also at part load. So for all different operating conditions of this installation, the unit will need a higher pump flow rate going through the heat exchanger, generating a higher pressure drop. If you have temperatures in your bedrock, as in this case, so that you can actually use it as free cooling, that also means that the capacity has a limitation, which means that you will have to operate the heat pump or chiller, adding on compressor cooling more hours of a year. So that's also increased energy consumption, of course. And then if you sometimes then you will reach the maximum capacity of the heat pump or chiller, and to compensate for that, you will have to reduce the evaporation temperature or increase the condensation temperature, which then influences the COP of the heat pump or chiller negatively as well. So again, all of this goes in the same direction, that the energy efficiency goes down. If you work with free cooling, natural free cooling, and using the bedrock, as in this case, as heat source as well, then you will always deliver, let's say, the wrong temperature. You will always have a deviation from what's specified to what you actually deliver to the bedrock. So if you run it for free cooling in the summer, you will store lower temperature in the bedrock, and when you don't turn it around to use it as heating source, you will not have as high temperature available. Again, all of this leads to an increased use of energy. So all in all, undersurfaced heat exchanger in this case doesn't perform, which generates higher operating cost. So if we look at this from the perspective of operating versus capital investment. So of course, the heat exchanger, which was sized with the market tolerances, is the red dot, and the green dot is what was actually specified. In this curve, I've simply added on additional operating cost per year. So the green line here is basically, this is when the installation operates as it was intended. There is no additional operating cost thanks to because of the higher pressure drop or underperformance of the heat exchanger. But if you look at the cost optimized unit, the one which is sized with this market tolerances, as we talked about earlier, it will of course be available on the market at a lower price level for investment cost. But when you look at the yearly consumption of electricity, then you have an additional cost on the operating point. And we look at this, I've been doing a lot of this analysis, and typically with the electricity cost that we've had, nowadays it's even higher. So this would actually be the turnaround for the additional investment would be shorter. But typically we end up in a payback of getting the right design being something like 1 to 2 years, typically. That is where the undersurfaced or cost optimized unit will start to cost more money thanks to the additional operating cost yearly. So it makes sense to actually get the performance you have asked for. Yes. So, okay, now we talk about market tolerances in sizing and a lot of uncertainty. And that is what we've seen. Actually, it all started to be very clear in the US market in the late 90s or early 2000s. And the first, or the trend was seen that a lot of these high-end buildings, skyscrapers, they couldn't cool enough in the summertime. So every equipment, according to the tech spec, was delivering what was asked for, but still the temperature was not met. So basically, even if the chillers was operating at full flow rate, they couldn't achieve the 20 to 21 degree set point in the office spaces or in the residential spaces. So they backtraced it and saw that there is air handling systems, there are duct systems and heat exchangers that actually were underperforming and couldn't reach the temperatures that they promised. So to get around this problem, the industry itself started a community to discuss it, and it was then handed over to an organization called HRI. HRI is equivalent to Eurovent, but in US, and has a global scope. So HRI started up a certification program for this equipment, so the plate heat exchangers, to ensure that you, as a customer, when it's certified, you know that you get the performance you have asked for. There is no more guesswork. So you should look out for this logo, HRI certified. That is the type of products you would like to have to ensure that you get the performance you have specified in a project. So a little bit more information about HRI in the performance certification program. So there is 2 certification programs that HR has for plate heat exchangers, one for brazed and fusion bonded heat exchangers, which is called LLBF, and one for the gasketed heat exchangers, which is called LLHE. What HRI does basically is that they give a guarantee or a warranty that the heat exchangers that are included in the certification program, they deliver the tolerance, the thermal performance and the pressure drop that are inside of the scope of the certification program's tolerances, making sure that all suppliers deliver the same actual performance. So as a customer, basically, you don't have to know anything about the product. You can only quote HRI certified, and then you are getting a guarantee from a third party that any supplier that delivers the certified heat exchangers will deliver the same performance. And of course, that's a good thing. Basically, we see them as making sure that you don't compare apples and pears in a quotation process. You get apples, or even they ensure that you get green apples if that is what you ask for, to make it even clearer. So HRI is your friend in this whole procedure. Just to slightly more background. So before entering the certification program, there is a qualification process, which is, of course, very good to have as a customer, to know that you have all suppliers have been validated from the same reasonable parameters, being able to supply and have financial strength and so on. Then the really central thing for me as an engineer in this certification program is that HRI on a yearly basis, they test units in test rigs to validate that they actually deliver the performance that they have claimed to do. And if you don't deliver the performance, if you fail to deliver performance, there are direct consequences, financial consequences stated into the certification program to make sure that everybody plays according to the rules of the certification program. So all of this together, the qualification process, the yearly annual testing, and the penalty systems connected is a very good incentive for suppliers to follow the rules, basically to bring the performance the customer asked for. Scope-wise, HRI is covering basically everything within HVAC, so it's quite media-wise, it's water, seawater, and glycols, which is the most common ones used in HVAC applications. Flow rate is very big, 1260 liter per second, so which turns into a huge capacity. So one unit can have up to 70 megawatts, and it's very seldom that we see HVAC applications having more capacity than 70 megawatts. Very, very seldom. So basically, if it's an HVAC application, you can demand HRI performance certification. And how do you do then? It's very simple in a project. It's one sentence to write into the specs. You only say that the heat exchangers from our project, they shall be having their performance certified in HRI liquid to liquid heat exchanger certification program, or liquid to liquid brazed and fusion bonded certification program, depending on if it's a gasketed or a plate brazed and fusion bonded heat exchanger. But this sentence is what I would recommend anybody all the time to write into a spec for a project, given that it's water, seawater, or glycol. used as the operating media. So it doesn't work with oil or two-phase. It's only one phase, water to water, glycol and seawater. The additional value then is that if we compare a technical specification that is certified, you will get much more data than what you get in a usual tech spec. And this is demanded also from the certification program to ensure that you hand out all details of your product. And it should also be traceable like this. You should be able to see the software version, when it's made, and then there should always be the disclaimer with HRI certified logo on the tech spec. And this is how you can determine that you have received a certified design that is surveilled by this third party. So I think it's quite simple actually to get the performance and make sure that you get it without having to be having a PhD in heat transfer yourself. Then you can just specify HRI, make sure that it's specified clearly with this sentence. Then you enforce. Many times it's a consultant that specifies, and then an end customer or installer that purchases the equipment. So of course it needs to be enforced for the purchasing person, if it's a contractor, installer, or even internal purchaser, that they also put this in writing in their requirements when they send a request for a quotation. And then a small warning is that there are some people in the industry that actually tries to fool people. HRI, it all started with a rating standard. So this it's a small Bible which is called HRI Standard 400. This is a text that describes the testing procedure, how to test and rate the performance of a heat exchanger. And sometimes suppliers would actually claim to be HRI certified by making references to a standard 400, saying that yes, our units are designed in accordance with the tolerances of this program, but then they are still not included in the certification program. So the unit would not be included in the yearly testing and all the functionalities that is included in the certification program. So you should always be very accurate, saying the unit should be in the certification program, not taking false claim that you are designed according to the tolerances of the rating standard, because that gives you basically zero value. So that is, I think, more or less it. I think it's quite clear. The message is that you should work with third-party performance certification. It's needed in this industry, unfortunately. Then when talking to end customers or consultants or getting information in quotations from some of our competitors as well, there is a lot of objections that I get. And I was just trying here to figure out 5 of the most common ones that I heard. And I think I have a quite good answer for all of them. And the first comment is always in the market that if you buy a HRI certified heat exchanger, it's much more expensive than a standard unit that is not certified. So hence, conclusion would be that the performance certification program adds cost to the heat exchanger, which it doesn't. If I compare a unit that is certified versus non-certified with the same number of plates, same frame, same everything, the additional cost is below 1% or even 0.1%, because the heat exchanger is basically the same. The difference in this case is probably that the installer is comparing a unit that has been sized with this market tolerances compared to a unit that is correctly sized. And that is where the difference in cost comes. So it's not the HRI unit that is expensive, it's actually the alternative unit that has been undersurfaced. Secondly, many times we then hear that, okay, this is a way to brick wall, there is a few suppliers available only, and then I will feel very limited into it. But right now there is 32 suppliers available, I would say, in the European market. All of the major suppliers found in the market can and are members of the certification program. And you can find all suppliers in this link below, hridirectory.com. And you can scroll down to LLHE, Liquid to Liquid Heat Exchanger Certification Program, and you will find all suppliers available there. Original supply is also something that I hear, maybe not in the European market, but others. And of course, there is no limitation where we can supply from any factory around the world. that is the beauty of this. HRI is verifying that the design is correct. And then if you deliver the same unit from any factory, that is what they're going to check and verify. Verification is something that is quite good in some markets. Actually, what you can do as a customer, if you are having doubts that the units are in fact designed correctly, even if they are certified, of course I could lie. Then there is a verification process, and HRI, they hold a copy of the software, sizing software of all suppliers. So you go into their website, you download a form, send it into HRI. They will have an engineer that will check and recalculate the unit and verify and stamp it and send it in return saying, yes, we have the software which we use for determining the units which we are testing, verified by testing. We can confirm that this unit will be within the tolerances of the program. And then the last one, this cost is actually a burden for the suppliers. It's not a burden, I don't know, that might be the wrong word, but the cost for a customer is zero. It's covered by us, the suppliers that are members of the certification program. So that's really good, of course. So just the conclusions here very shortly. So the summary is that undersurface heat exchangers that are not delivering the performance, unfortunately, in many markets are being, let's say, the standard solution used in the HVAC market. When a unit doesn't deliver, it can be compensated by adjusting evaporation temperature, for instance, on the chiller, but that will always drive higher energy bills. So the whole system efficiency is hurt, leading to higher cost. And of course, the cost, additional operating cost is there 24/7, 365. So the total cost of increased operating cost, as showed in the earlier graph, is typically 1 to 2 years is where you have the break even for the additional cost of the correctly sized unit. So, and there is a certification program. It's available. It's there to protect you as customers or consultants to actually be able to validate that you get the performance that you have calculated, the needs you have decided that you need for your installation. So I think that's, I will skip through a couple of slides here before I go over to Isma. So I think and hope that you also see this potential that we have with HRI performance certification. You shouldn't trust me as a supplier. You should trust someone who watches what I do, basically, this non-biased third party. And as I said, all suppliers basically in the European market is in the certification program. So you just go ahead, specify it, enforce it, and buy it. That was all for me, actually. And then I will hand over to Ismail Usman, who will take you through a little bit about heat exchanger technology from Alfa Laval.
Thank you so much, Morten. Nice presentation. You can always be sure with HRI. Let's remember that. And I would also like to remind the audience that we will have a Q&A in the end. We have some questions coming in. The questions will be totally anonymous, so you don't have to be afraid of any questions. Just put them in the chat and we will answer it during the Q&A session in the end of this webinar. Welcome, Usman. The stage is yours. We are eager to hear about the energy hunting for energy efficient buildings. Warm welcome.
Thank you very much, and I'm really looking forward to sharing information on ways to save energy and reduce carbon emissions. In the next 20 minutes, what we're going to do is take it into two parts. First, we're going to look at how the Alfa Laval heat exchanger design helps save energy and save money in terms of OPEX and CAPEX costs. And in the second section, we're going to look at water-cooled chillers, how we can save with turning the chiller off and also condenser protection. But myself, I'm 30 years plus into working with Alfa Laval, always with heat exchangers. A lot of my years have gone with distribution management, but energy hunting is definitely a passion of mine. So if we go into these unique features which make Alfa Laval more efficient, energy savings, and also reducing CAPEX and OPEX costs, we will focus today on three of them. Now, the first one, you see the symbol here, which is called curve flow. And this is very, very important for the distribution of the fluid inside the channel. Because if you look at the image here, where we look at water flowing inside the channel, usually water will take the shortest route, and that is enter from, let's say, the top left connection and take the shortcut to the bottom left connection. Now, if the heat exchanger doesn't have a very good distribution pattern, and that is to distribute the fluid into all the areas inside the channel, then we will get fouling and we will get underutilization of the available surface area. So this is a patented, unique, new feature of Alfa Laval, which ensures performance and that we can deliver what Martin mentioned just before, exactly the performance that's required for the duty. I mean, these features are enabling us to be able to deliver that performance. The second feature is the Omega port, and you notice that the port shape of the Alfa Laval plates are actually non-circular. And what this does, it reduces the maldistribution inside the plate pack, and also it's a bigger opening. It's instead of a circular one, which makes that the pressure drop lost in the ports is of course waste. We want the pressure drop to be used for heat transfer. So this helps the performance and the energy savings immensely, the Omega port. And the third one, I think in HVAC, we have a lot of equal flow rates from the hot side to the cold side. But there are applications, and we see that when you have non-equal flow rates, in other words, one fluid is higher flow and the other fluid is a lower flow. Usually the lower flow, because the channel sizes in a plate heat exchanger, and this is all manufacturers, and also before it was rather, the channel sizes are usually equal. And when they're equal, the lower flow rate will have faster fouling because of lower channel velocity. So these three features help to reduce fouling, they help to save energy and optimize the use of your pump energy for better heat transfer. So how does the distribution pattern help us to save energy? If you look at another brand, not Alfa Laval on the left, you can see if they have a poor distribution pattern, as you see here, then we will get dead spots and the fluid not reaching all the extremities of a channel. There are local brands and brands that are manufactured in China, like copycat units and such, which are actually utilizing the surface less than 50% of the available surface, because they don't have a very good distribution pattern. And the consequence of this is really that you get underutilization of heat transfer area, but also you get the start of fouling. And if you, let's say, a part load with a cooling tower application, half load means quarter the velocities, and then the fouling, which begins at this dead spot, moves to the left, 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 until the water in this channel is just going from port to port. And this is not what we want. So that's the importance of the Alfa Laval curve flow, which is developed only in the last 2-3 years, and is available with all our products, all our model sizes of heat exchangers, which is very, very good. Now, a little bit at how does Alfa Laval secure that? Of course, it's a lot of R&D, but please remember, all of these features should not demand more than 10% a price difference compared to other brands. So if you have an offer of Alfa Laval being double the price or 50% more, etc., there is something wrong. And the reasoning is what Martin explained. It's the price tolerance design that is happening. So all of these features, what we claim is that it should only make a difference to the price of the Alfa Laval heat exchanger by a maximum of 5 or 10%. If not, there's something wrong. So how does Alfa Laval achieve this? You see this distribution pattern here. What Alfa Laval does with the curve flow, you see that there's a curve here. This is a short distance, and the fluid, the water would like to go in this short distance, which is usually low resistance to flow. But if Alfa Laval makes the resistance to flow along this short distance equal to that of this longer distance, where usually water doesn't want to go, then equal resistance all along this area means that we will make sure that the fluid does go to these extremities. And if it is not, like this one is a non-Alfa Laval distribution pattern, you will see that at part load, for example, the fluid will only travel part of the plate surface. Now, the consequence of this, I'd like to add, is that poor distribution is energy wastage. Why? Because we have a heat exchanger in front of us, and we have a pump, and we want to pump this fluid through the heat exchanger and have effective heat transfer. And if we don't utilize the heat transfer surface that is available, it's a waste of pump power. So in other brands, what you see is that this plate, for example, the cold fluid is traveling through, and on the next channel, the hot fluid is traveling through. So the cold is going down and the hot is traveling up. Now, if you don't have good distribution pattern here, what happens is that the cold fluid only uses the left-hand side of the channel, as you see here, and the hot fluid uses only the right-hand side of the channel. And basically, the two fluids seldom see each other for effective heat transfer. So the heat transfer surface that is available is not fully utilized, waste of pumping power. Most likely that there will be fouling, and that's going to mean that you have to open and clean the heat exchanger, or the fouling is going to increase your pump pressure and pumping costs even more. So to sum up, it's Alfa Laval does have a lot of features, and all these features, the end user should not pay more than 10% of a competitor's heat exchanger. And what they do, these features, is that they provide excellent distribution through the channel, which ensures that the Alfa Laval heat exchanger stays clean longer. So that would be the summary of, going into the kitchen of plate heat exchanger design and operation. So with that, I also want to touch on some of the applications where Alfa Laval can help with energy savings and decarbonization. We'll look at savings around chillers in the next 10 minutes. So savings around chillers. Chillers are one of the largest electricity consumption and cost to run a building. It really needs further attention, how we can minimize this huge cost in your operating costs. Now, this is a look at a unit that we have installed in Turkey. It's in an MR building. It's a manual system, so it's a free cooling application. It doesn't have any automation. There is a manual valve. For a month in winter, the chiller is turned off, and the cooling tower cools the building, the hotel, the shopping center, and other office buildings, with the help of this plate heat exchanger. So we're going to look at now condenser protection and free cooling with chiller turnoff. Now, what's happening? We find a lot of chillers that are working with water-cooled condensers, and the condenser of the chiller is receiving cooling tower water, let's say at 32 degrees Celsius, and returning back at 36. And the cooling tower water is used to condense the gas. Now, the problem is with this, I will show you a little later as well, that the chiller condenser has to be cleaned annually, because calcium carbonate or scale in the cooling tower water actually cooks inside the condenser tubes. It becomes solid, and this reduces the efficiency, reduces the COP, and hence does require cleaning because it's higher electricity costs. Now, what we're suggesting as a savings for the HVAC industry is to put a plate heat exchanger between the chiller condenser and the cooling tower. What will happen is that the condenser will receive 1 degree Celsius higher cooling water temperature. And whatever the cooling tower water is, the condenser will receive 1 degree higher. But the good thing is that this loop of between the condenser and the heat exchanger is lifelong clean, and the condenser never loses efficiency due to calcium carbonate. So we have an opportunity to save electricity on the condenser and also to allow for free cooling. Now, if we look a little bit deeper into this application, what we are doing is there is a double benefit of this heat exchanger. One is to protect the condenser. You can see here that it is serving the condenser with the cooling tower water. Let's dig a little bit into this, and after that we look at free cooling with a case example as well. Now, the problem with cooling towers, really, friends, is that cooling towers are never well maintained. And they have a buildup of calcium carbonate. As the water as the water evaporates, as you see here, the calcium carbonate and chloride ions actually accumulate. It's like a mineral deposit box. The only way to remove these is really to flush the cooling tower regularly. If we don't, what happens is that the calcium carbonate actually, with the cooling tower water, goes into the condenser, and on a hot surface, it actually precipitates, comes out of solution, and sticks itself onto the hottest surfaces. And that is typically the condenser. Now, if we look at calcium carbonate, it actually behaves opposite to that of household sugar. So if you have sugar, this bold line, at cold temperature, 35 degrees at room temperature, it's at solid state. But if you put your sugar cube or into your tea or your coffee, the hotter the temperature, it will actually melt faster. Being opposite to that of sugar, calcium carbonate is actually invisible and in solution at low temperatures. So you never see it around the cooling tower. And calcium carbonate actually precipitates at higher temperatures. For example, your kettle at home. The base is with hard water can have calcium carbonate accumulated there. It's because of the temperature, friends. Now, what we're proposing, as I showed you before, is to break the circuit with a heat exchanger. The calcium carbonate here stays in solution because the wall temperatures are under 40. And where the condenser is between the heat exchanger, we do need a set of additional pumps, yes, but this is lifelong clean. The condenser, the chiller efficiency does not drop because of this calcium carbonate. And even if it's 120 degrees superheated gas, the refrigerant gas, there is no calcium here. So this is a great way to save in electricity costs and also saving maintenance costs. But electricity is by far the biggest saving here. Now, if we look at the second effect, one, this heat exchanger, being an interceptor, actually protects our condenser. And this is in summer condition where we have ambient temperatures of maybe 10, 15, 20, 50, whatever. So this is the summer operating condition without the free cooling. In winter, when the ambient temperature is below 6 degrees Celsius, again, remember the heat exchanger is designed with a 1 degree approach. So if the cooling tower water is at 6 degrees Celsius, the heat exchanger will provide 7 degrees Celsius, which is actually the job of the chiller. So if we can get 7 degrees Celsius from the cooling tower, it means that we turn the chiller off and we provide a 7 degrees Celsius to the air handling units, the fan coils, and help cool the building during winter. So that's the double effect. Now, when it comes to the savings, we have a rule of thumb that we use, and we assume, for example, a COP of 7 on average for water-cooled chillers. And in this example, if we have a chiller which is 2000 kilowatt with a COP of 7 running half the year, 4,000 hours per year, this is a typical illustration of the savings that you can make with this 2000 kilowatt chiller cooling capacity. We basically divide the cooling capacity by the COP, so it's 2000 divided by 7, and this is the electricity that's used to run this chiller. So what is the cost of running the chiller? Of course, we need to take into account this 4,000 hours a year and the cost of electricity. I've taken 0.17 because at the last information, I think in Spain, it was 0.17 euro. So running this chiller 4,000 hours a year is 180,000 euro. Now, the savings with condenser protection is about 10%. The savings with turning the chiller off, say 400 hours a year, is again about 18,000. So totally 36,000 euro savings per year with this application, which is a fantastic amount of money. And the payback period is well under 1 to 2 years. Now, if we look at sustainability and carbon emissions, if we're not using the electricity, if we are turning the chiller off, of course, we're not going to release so much carbon dioxide into the atmosphere. And the way that we calculate that is I've taken Poland, and for Poland, the amount of carbon dioxide emitted per kilowatt hour of electricity usage is about 736 tons per kilowatt hour, but in kilograms, it's 0.736. Now, carbon emission factor, a quick guide to how to calculate that and work with that is very much that it's information. The carbon emission factor is published in the internet for a given country on average, or a city, town, province, etc. It depends very much on how that electricity is produced. For example, if the electricity is produced by using coal, it will have a very high carbon emission factor per kilowatt hour. If it's electricity is produced with nuclear or hydroelectric or solar or wind power, it's going to be lower. It could also be a mixture as well. So it is information that's published on the internet. And with this particular application, 2000 kilowatt cooling capacity, divide by the COP, times the hours running and the carbon emission factor. This chiller running 4,000 hours a year is releasing 841 tons of carbon per year, 841 tons. Now, if we can save 10%, it's 84 tons. And this is a major saving and a good sustainability focus. I don't know if we have consultants in this team, but our biggest challenge is to design more efficient buildings and to look at all the opportunities of saving energy and also have a green building with less carbon emissions, as we've shown here. Now, with that, I'd like to, in the next 2 minutes, run through a case which is very, very successful. It was installed about 2 years ago, and the installation is in Korea, South Korea. It's at a pharmaceutical company called Chongkungdam. It's Southeast Asia's or Asia's biggest pharmaceutical company. And the return on investment was 1 year, but the customer said it's actually less than 1 year. So that's very, very good result that we have seen. This is a quick look at the heat exchanger. It's the same heat exchanger with 3 different views. So this is an Alfa Laval plate heat exchanger working between the between the cooling tower and the water going to the air handling units. And this is a HVAC application in the pharmaceutical company it is. So what we have here is 1, 2, 3, 4 cooling towers, which are providing cold water down to 2 chillers. One is here, the other is here. And what our Energy Hunter partner in Korea has done is installed an Alfa Laval plate heat exchanger here. And there is no automation. It is, again, very, very manual. And what they do is they divert the cooling tower water at 6 degrees Celsius, going to the plate heat exchanger and then returning to the tower. And on the other side, to the air handling unit rooms here that you see, they provide 7-degree water on the other side of this heat exchanger. So very, very effective. The unit supplied is about 3 meters tall, 200 mil connections, and highly appreciated by the end customer. So it's not only a new project, but existing HVAC projects where there is a chiller and there is a cooling tower. I mean, there is no time to waste. It depends on your outside air conditions and your cooling tower temperature as well. And to be able to advance further, we can help you with Alfa Laval's Energy Hunter partners that are globally working on these solutions. It is simply to provide to Energy Hunter at alphaval.com. If it's a water-cooled chiller, what is your ambient temperature? And the location we would like to look at on the internet, you know, how many days you will have temperature under 6 degrees Celsius for you to water. Capacity of your chiller, your running hours, and we provide a document like this, which is a proposal with the payback period showing with all the values that we have put together so that you can advance with turning the chiller off in that sense. So to sum up, energy savings, absolutely crucial with every step that we take, and energy savings is adopted into our heat exchanger design, especially distributing the flow through the channels, avoiding fouling, minimizing fouling, keeping pump costs to a minimum, and making sure that the heat exchanger is efficient with the pumping power that we are using. And secondly, the application of protecting the condenser. One heat exchanger can also in winter help to turn that chiller off. And the savings, of course, how many days a year that you can turn it off. With that, I finish and I hand the word to Anna to take any questions that we may have.
Thank you so much, Ismail, for this nice presentation. And I'd like to remind you all that please put your questions in the chat and we will answer them. So I'll just give you a short summary. So this session, this webinar, were about how to save energy and reducing carbon emission in HVAC. There is a huge energy challenge and climate challenge, and we are in this together. We need to collaborate. We need to work over sectors. And we at Alfa Laval, we're happy to be a part of this, facilitate collaboration, and also facilitate knowledge among different sectors. Alfa Laval, we're determined to be carbon neutral 2030. And of course, we are learning a lot during this trip. And we are also learning a lot together with our customers. We see the sustainable city as a very, very important area to work with, decreasing the carbon emission, and also work together with you to decrease the cost of energy. And when it comes to the sustainable city, of course, use the electricity when it's needed, for example, for the transportation, for the green transition of the process industry, for example. But we can heat our buildings and work with our comfort heating with heat networks, reusing energy, using renewables, and also to work with energy efficient buildings, where we have seen some examples so nicely presented by Ismail. And then Morten gave you the presentation around AHRI. You can always be sure there are a lot of designers designing with market tolerances. This will always lead to a higher operating cost and a higher carbon emission out in the air. We need to work with certification, and AHRI is an excellent tool for this. So always ask for AHRI. And Ismail, very nice presentation on Alfa Laval being experts on heat transfer. We put 2.8% of our revenue into R&D. Very important to develop continuously the best heat exchangers on the market. And we can see that, for example, in the curve flow, the special Alfa Laval pattern, we see it in the Omega port and the flex flow. And feel free to talk with your local Alfa Laval employees if you want to know more about our branded features. And those nice examples, Ismail, how to save energy around water-cooled chillers, both, of course, money and carbon emission, and also carbon emission electricity savings when it comes to free cooling. And also this very nice example of how we can actually calculate on the return on investment, Ismail. And this, we can all have a free copy of the return on investment sheet. So that was a short summary. If you then are very curious to hear this again, maybe you missed something, there will be this webinar will be placed on YouTube, so you can see it afterwards. And this will actually be the end for the YouTube listeners. And we say thank you to the YouTube listeners. And the rest of us will go into the Q&A, where we discuss a little bit further.